Okay, well, our lab that was originally scheduled for today was, or for this week, was going to be an oxidation reduction titration. But we're just going to kind of walk you through the mechanics of what would have happened had we gone to the lab. Now, in order to balance the oxidation reduction reactions and to really understand the pre-lab for this, you need to watch the precursor lecture that I made on oxidation reduction reactions. I think I sent you the link to both. So if you're watching this first, stop. Go back and watch the oxidation reduction lecture and then do the lab. This is only about a 20-minute video, 20 or 30-minute video, and it doesn't take long to get through it. And the first video will definitely help you do the pre-lab. All right, well, let's get to it. First of all, the reaction that we had planned for you today was this one, the reaction of potassium permanganate with potassium hydrogen sulfite. And it's an oxidation reduction reaction, but one thing I should mention, they talk a lot about oxidizing agents and reducing agents in your textbook, and it always is a point of confusion. But here's the thing. An oxidizing agent is something that steals electrons. It's acting as an agent to oxidize something else. In that process, it itself becomes reduced. For instance, potassium permanganate is considered to be a pretty good oxidizing agent. It's that purple stuff we threw in the lake to eat up the algae. Well, that's because the permanganate likes to steal electrons. The +7 state of that manganese likes to go down to like +4, and to do that it needs to pick up electrons, and it'll steal them from other compounds. So that makes it a good oxidizing agent. But notice that during that process, the manganese itself gets reduced, because those two things always happen simultaneously. Same goes for a reducing agent. The reducing agent is the species that actually gets oxidized, because the reducing agent is pushing electrons onto something else to reduce it. In the process, it loses electrons. So you can just kind of think of it, as an opposite day. The thing that gets oxidized is considered the reducing agent. The thing that gets reduced is considered the oxidizing agent. I won't say that twice because it just confuses the whole issue. So in this case, our oxidizing agent, permanganate, is going to go from +7 down to a +2. It's actually going to gain 5 electrons in this process. Let me grab a fresh piece of chalk here. Our reducing agent, KHSO3, where the sulfur is in its +4 state, is going to go down to KHSO4, where the sulfur is in its +6 state. All the other sulfurs that are in here, these other sulfates, they're just kind of along for the ride. They're coming in with the sulfuric acid. So it's the important players are the manganese and the sulfur that's in the KHSO3 and the KHSO4. All right, well, let's put our arrows in here. Now notice something. This is a molecular equation. It's not an anionic equation. So we don't get to add anything. I think everything we need is already here in the equation. Well, the permanganate is going to go from +7 down to +2. So here's our reduction. It was a gain of 5 electrons. On the other hand, the KHSO3 became the KHSO4. I'm going to do kind of a circuitous arrow here. There's our oxidation. A loss of 2 electrons. All right, well, this is a problem because a loss of 2, gain of 5. The only way to resolve this is go to a common multiple of 10. Well, that means we're going to have to double our reduction half reaction. So that means doubling the MnSO4, doubling the KMnO4. I'm going to have to 5-tuple my oxidation reaction, take it up by a factor of 5 to make this 10. So that means 5 in front of the KHSO4, 5 in front of the KHSO3. Now remember, I'm married to those 2s and 5s. They're carved in stone. I cannot change those. But we've got a lot of other mass here to balance. And again, we're not trying to balance charge. This is not an ionic equation. So let me get rid of our arrows. We've resolved this electron imbalance just to neaten things up a little bit. And I'll get rid of our oxidation numbers. We don't need those anymore. We've got all the electron exchange balanced. But check this out. I mean, now that I've tied in those 2s and 5s, the thing that's really going to tip the scales here, it looks like the potassiums might be my next play, because the potassiums come in here and here, and I'm tied to those two numbers, that 2 and that 5. So that means there are 7 potassiums on this side that have to be accounted for on that side. Well, there's 5 of them, and there's the other 2. So I've got my 7 potassiums. That means really I don't really have a play here. I'm going to have to leave that as a 1, because that locks the potassiums in. But that does also lock in the sulfate groups. Remember I said there was a lot of sulfates that are just along for the ride, and they're coming in this vehicle as H2SO4. Well, we've accounted for these 5 SO4s. They came from these 5 SO3s, so those are not going to be counted. But I've got 2 other sulfate groups here and 1 there. Well, that's 3 SO4 groups that I have to bring in this vehicle. So a 3 in front of the H2SO4 would balance that sulfate group and these 2. All right, so now all of those sulfates are taken care of. The last play I have is water. Well, if I count hydrogens on this side of the arrow, it appears that I've got 5 here, and then here's another 6. So I've got 11 hydrogens on this side. 5 of them appeared here, so that means there's still 6 unaccounted for. All right, well, that means 3 waters would balance those 6 hydrogens. Well, I'm out of places to play, so hopefully the oxygen's balanced. Well, notice I've got 8 here, 15 there is 23, and another 12 is 35 oxygens on the left side of the arrow. Well, there's 8, there's 20, that's 28, 4 is 32, 3 is 35. 35 oxygens on both sides. Now, the reason we chose this reaction for you to do, we wanted you to, again, practice balancing redox equations, but the reaction of potassium or hydrogen sulfite, which is a nice clear solution, and this very, very purple permanganate, has kind of a built-in endpoint, because once the last of the permanganate gets eaten up, this manganese sulfate is colorless, it's clear. So the minute you reach the endpoint of this titration, where we dribble in potassium hydrogen sulfite into a solution of potassium permanganate, suddenly the purple color completely vanishes when you reach the endpoint. All right, so we chose this because, again, no indicator required, nice easy titration, very clear distinct endpoint to hit. And we can figure out then how strong the permanganate solution was by knowing how strong our titrant was that we dribbled in there. Just like an acid-base titration, only in this case, it was an oxidation reduction titration. Well, let me get rid of this and I'll elaborate a little bit about normality. If you remember, we used that in our acid-base titration days. We're going to apply that same concept here to oxidation reductions. Okay, just a little reminiscence here. Back when we did our acid-base titrations earlier in the semester, we introduced this concept of normality, which is a little subtly different than molarity. For instance, normality is defined as the number of moles of H plus a solution has in it per liter. Now remember that some acids bring maybe 1 hydrogen to the dance for each molecule. Some of them have 2, like sulfuric acid, H2SO4. Some have 3, like H3PO4. So 1 mole of an acid doesn't necessarily reflect its true acidity. You have to also incorporate, well, how many hydrogens is that 1 mole bringing per molecule? So, for instance, if we had a 1 molar solution of H2SO4, if I took a certain volume of that, say 1 liter of that bottle, and took that molarity times the volume, that would tell me the number of moles of H2SO4 that are in that bottle. But normality says, well, we need to multiply the molarity times the number of hydrogens it has, because that would more accurately reflect its true acidity. So if I multiplied that molarity by 2 and said that was the normality of the H2SO4, well, that times the volume doesn't equal the moles of H2SO4, it equals the moles of actual H pluses that are available. That normalizes everything down to just 1 common denominator. the hydrogens. With the base, it's exactly the same. It's hydroxides that reflect the normality. What's the total head count of hydroxides? So let me erase this for show you something else. For instance, if I had a 1 molar solution of HCl versus a 1 molar solution of H3PO4, this one has 3 times the neutralizing power that this solution would have. Because the fact phosphoric acid has 3 hydrogens, it could donate in a neutralization type reaction. So it turns out that if I multiply the molarity times the number of hydrogens it has, that tells me the normality. So for instance, this would be 3 normal H3PO4, whereas the HCl would simply be 1 normal HCl. This number does more accurately reflect than the true acidity of the solution, or its ability to neutralize a base, let me put it that way. And it does then normalize everything down to just the common denominator of the hydrogen ions. Same thing goes with bases. It turns out that if I had a 1 molar solution of sodium hydroxide versus a 1 molar solution of barium hydroxide, where it's got twice as many hydroxides available, this is definitely more basic than the sodium hydroxide, even though they're the same molarity. But again, normality takes care of that. It multiplies the molarity by the number of hydroxides. So this would be 2 normal barium hydroxide, where the sodium hydroxide would still just be 1 normal. All right, now the reason that we did this was because in any acid-base neutralization reaction, it really doesn't matter how the hydroxides got to the dance or how the hydrogens got to the dance. At the equivalence point, the moles of hydrogen have to equal the moles of hydroxide. That's at the neutral point. Well, the moles of hydrogen then would be defined as the normality of the acid times the volume of acid used. Because again, the normality has taken into account already how many hydrogens were attached to each molecule and has now represented that as just a total head count of hydrogens per liter. The normality of the base did the same thing. It just took a total head count of hydroxides, regardless of how the base showed up, whether it came 3 in a package or 2 in a package. Ultimately, they just took a total head count of how many hydroxides are there, times the volume of the base. So we came up with this nice, easy equation for you to do titration, where you didn't have to think of the stoichiometry of the reaction. You didn't even have to stop to think, well, how many hydrogens did the acid have? Because that was already taken into account with the normality. We didn't have to think, well, how many hydroxides did the base have? That's in its normality. So all this says is the number of moles of hydrogen has to equal the number of moles of hydroxide. Now, let me show you how we apply this to oxidation reduction reactions. This is a tug of war over electrons. Okay, if we define one equivalent of an oxidizer as 1 mole of electrons stolen. So if I had an oxidizing agent and it was willing to steal 1 mole of electrons, I'd call that 1 equivalent of oxidizing power. Okay, well, 1 equivalent of reducer would be the ability to give away 1 mole of electrons given. All right, so in our reaction today, what we were looking at was our oxidizing agent was manganese going from +7 down to manganese +2. In order to do that, it had to steal 5 moles of electrons. So that means each manganese +7 had 5 equivalents of oxidizing power. It was willing to steal 5 moles of electrons. It would be like an acid that has 5 hydrogens to give up to the solution. So if we knew the molarity of the manganese, how could we calculate its normality as an oxidizing agent? Well, just like before, we would multiply the molarity by the number of equivalents of oxidizing power it has. Just the same way we multiplied the molarity of an acid by the number of hydrogen equivalents that it has attached to it. All right, so in that case, we could say that a 1 molar solution of KMnO4, at least in this situation where the manganese is willing to steal 5 electrons, is equivalent to a 5 normal solution of KMnO4. All right, so again, we've kind of applied the same idea that we did with acids and bases to oxidizing power, equating the moles of electrons stolen as hydrogen ions that would be on an acid. Well, what about our reducer? Could we do the same thing? We could say, for instance, one equivalent of reducing power is 1 mole of electrons given. Well, today, our KHSO3 became KHSO4, where the sulfur went from a +4 state to a +6 state, and it had to give up 2 moles of electrons in order to do that. It got oxidized, but that makes it the reducing agent. Okay, well, if that's the case, then 2 equivalents, that would mean a 1 molar solution, at least in this setting of KHSO3, is equivalent to a 2 normal solution of KHSO3 because of its ability to give away 2 moles of electrons per mole of KHSO3. All right, well then, again, it would be like a base that had 2 hydroxides on it. We multiplied the molarity by its ability to give up those bases. Here, its ability to give up those electrons was used to calculate the normality. All right, well, in any oxidation reduction reaction then, the number of moles of electrons taken, we've just established, has to equal the number of moles of electrons given. Well, this would be the normality of the oxidizing agent times the volume of oxidizing agent used to equal the normality of the reducing agent times the volume of the reducing agent used. So you can understand the similarity here between the normality idea applied to acids and bases and the normality idea applied to oxidation reduction reactions. All right, so let's see how this applied then to our reaction today. Okay, this was pretty much how the lab was supposed to go. We were going to have you put some potassium permanganate in an Erlenmeyer flask and titrate it with some KHSO3. Again, it had a built-in endpoint because it goes colorless when it reaches its equivalence point, when everything has gotten oxidized. And again, when we balanced the equation, it was 5 KMnO4s to 2 KHSO3s, but again, that's been worked into the normality idea, so really all we need is this equation, the normality of the oxidizing agent, the KMnO4, times whatever mils of it we used, has to equal the normality of the reducing agent, the KHSO3, times however many mils of it we used. All right, so we just had you dribble in the KHSO3. Notice something here. We put our unknown this time in the burette and put our known down here in the flask. That's usually the other way around. Usually we've got our unknown down here. The reason we did it that way is we didn't want you splattering KMnO4 on yourself, and so it was much easier to put it down here in the flask than having you try to fill burettes with it. All right, so anyway, once we did the titration and we had the number of milliliters of the KHSO3 that it took to go colorless, it was really not much trouble to do the math here and figure out the normality of that reducing agent. We knew the oxidizing agent was 0.1 normal. We know how many milliliters we took for our sample. We had to take a 10.00 mil sample. And then we knew the number of milliliters, the reducing agent, from the burette. All we had to do is just dribble it in again until it went colorless. So I'm not going to have you go through those calculations. I mean, that's a pretty simple little plug and chug equation. What I'm more interested in is your ability to actually balance the oxidation reduction reactions. So if you would, just finish off the pre-lab. I gave you some tips earlier in the video. Go through those 6 redox equations, balance those, and if you wouldn't mind, just take a picture of that and submit it. Now, next week, we've got an electrochemistry lab, a galvanic cell lab that I'm working on for you, where we're actually going to make some batteries, measure their voltages, and do a couple little graphs. Since you don't have the computers there to do the graphing, I'm going to send you some graph paper with the axes already labeled and everything for you to do it the old-fashioned way. So anyway, I hope this wasn't too painful. Again, if you can get your pre-lab wrapped up and submitted in a timely fashion, that would help. And again, I'll either see you in lecture or next week in lab. So long.